Hi, this is Professor V.K. Patel. I welcome you to the video classes on basic electronics. In my last class, we have discussed about inverting amplifier, in which we have discussed the circuit configuration. In inverting amplifier, we use a negative feedback. The negative feedback, it means that output is fed back to the input, to the inverting terminal of the op-amp. And as I discussed earlier, the negative feedback basically it leads to the stability. Today we will discuss about the expression for the output voltage in inverting amplifier. Next to that we will discuss about non-inverting amplifier and its derivation for the output voltage. Let us start with the expression for inverting amplifier. Inverting amplifier, the circuit diagram can be drawn something like this, where the input is applied to the inverting terminal, output is fed back to the input through a feedback resistor, non-inverting terminal is grounded. Let us say input to the inverting amplifier is V1 through the resistance R1. Supply voltages are plus Vs minus Vs and output voltage is V0. Now let us derive the expression for the output voltage. For that reason, let us assume the current flowing through the R1 is I1, which is flowing from the supply voltage V1 to the output side through the resistance R1. Let us say this is the node X. Again, the current flowing through the feedback resistor RF is I2, and the current which is entering into the op-amp, let us say it is I in. Right? Now apply KCL at the node X. Apply Kirchhoff's current law at node X. What is the Kirchhoff current law? The Kirchhoff current law is incoming current at any node is equal to the outgoing current. So at the node X, the incoming current is I1 and outgoing current are I2 and I. So KCL equation at the node X, it becomes I1 which is equal to I2 plus IE. As we know that the input impedance of the op-amp is infinity. So therefore the IN it comes equal to the 0 as Rin is equal to infinity. Is it right? So as Rin it is the infinity, so it acts as an open circuit and In will be a 0. Now writing this KCL equation, I will get I1 is equal to I2. Writing I1 and I1 in terms of the voltages, I1 I can write it as potential difference divided by the resistance. The potential difference is V1 minus Vx. Let us say Vx is the voltage at the node X. V1 minus Vx divided by R1, which is nothing but the I1, because we know that the potential difference divided by resistance is nothing but the current, and I1 is the current which is flowing from the voltage V1, voltage source V1 to the node X. Hence I can write it as V1 minus Vx divided by R1. Similarly, I can write I2. I2 is the current which is flowing from the node X to the output. Hence I can write it as Vx minus Vout divided by RF. Now what is the Vx? The voltage at non-inverting terminal is 0, which is equal to V2, and by using the concept of virtual ground we know that Vx it must be equal to the V2, which is equal to 0, as V2 is 0. Is it right? So what is the virtual ground concept? So by using the virtual ground concept I can say that the voltage at inverting terminal must be equal to the voltage at non-inverting terminal. Voltage at non-inverting terminal is V2, which is grounded, hence it is the 0. Voltage at inverting terminal is nothing but the Vx, hence V2 must be equal to the Vx and it is equal to the 0. Substituting Vx is equal to 0 in this expression, we will get V1 divided by R1 is equal to minus V0 divided by Rf. Hence I can write output voltage V0 is equal to minus Rf by R1 into V1, where Rf by R1 is known as closed loop gain of an inverting amplifier. Here A CL, which is nothing but the closed loop gain, which is equal to Rf by R1. So here the gain of inverting amplifier is Rf by R1. Simply by choosing the values of Rf and R1, I can control the gain of the inverting amplifier, that is in a closed loop. Hence this is the benefit of a feedback. Right. So here the gain I can write as Rf by R1, and the negative sign, it indicates that the output voltage is inverted version of a input. It means that if I apply a positive voltage, I will get a negative voltage at the output. If I apply the negative input, I will get the positive output at the output side. If I apply the sine wave, the output voltage will be again a wave which is 180 degree out of phase with the input. This is all about the expression for the output voltage of the inverting amplifier. This is the expression for the output voltage, and this is the expression for the gain of a inverting amplifier in a closed loop configuration. Next to this, we will discuss about the non-inverting amplifier and the expression for the output voltage in case of non-inverting amplifier. How to draw the circuit for a non-inverting amplifier? Non-inverting amplifier in closed loop, right? So again we have the op-amp, we have inverting and non-inverting terminal. Now I need to apply the input to the non-inverting terminal. Let us say it is V2. In the earlier circuit, I need to simply connect or replace the V1 by ground. This is what the feedback resistor Rf, this is what the R1, and the output voltage I will get in case of non-inverting amplifier. Let us redraw this circuit so that I can easily derive the expression for the output voltage. Redrawing this circuit, this is inverting terminal, non-inverting terminal, non-inverting terminal. Here we have the feedback resistor Rf, this is R1, this is Rf, this is the node X, and voltage at this node X is Vx, and input is applied to the non-inverting terminal. So these are the supply voltages and output voltage. Is it right? The circuit it is set. So negative terminal, R1 is grounded, Rf is in between the output voltage and node X. Now from this circuit I can write the expression for Vx by using the voltage divider circuit. The voltage Vx, it can be given as R1 divided by R1 plus Rf multiplied by Vout. So voltage across R1, that is nothing but the Vx, which is nothing but R1 divided by total resistance R1 plus Rf multiplied by the voltage which is input to this voltage divider circuit, that is nothing but the V0. Now by using the virtual ground concept, the voltage at inverting terminal, it must be equal to the voltage at non-inverting terminal. The voltage at this inverting terminal is Vx, voltage at the non-inverting terminal is V2. Hence, by using virtual ground concept, I can write V2 is equal to Vx. Now substitute this V2 and Vx. So I can write V2 is equal to R1 divided by R1 plus Rf into V0. From this I can write V0 is equal to R1 plus Rf divided by R1 into V2, where V2 is the input to this non-inverting amplifier. Further, I can write this V0 is equal to 1. R1 divided by R1 is 1 plus Rf by R1 multiplied by V2. This is what the expression for the output voltage in case of non-inverting amplifier, where 1 plus Rf by R1 is the gain of this closed loop configuration, which is equal to 1 plus Rf by R1. And if you look closely, the expression for output voltage, there is no minus sign, which means that if I apply the positive input voltage, I will get the output which is positive. If I apply the negative, I will get the negative. If I apply the any waveform, the output voltage, it will be in phase with the input. And this is what the expression for the closed loop configuration of the non-inverting amplifier. Thank you. In next class, we will discuss the applications of the operational amplifier.